Today we're going to be discussing the kinematic equations. Up at the top of this chart, I go through what each variable means, and these five kinematic variables are actually pretty darn important, so I highly recommend memorizing them. And each variable has a meaning. So v sub I means initial velocity, v sub f means final velocity, delta x, which sometimes can actually be delta y or even delta d, stands for the displacement, a is acceleration, and t is time. Something I'd like to throw in here, though, real quickly, is the units associated with each of these. So velocity is measured in meters per second for both of these. V initial and v final will be in meters per second. Displacement typically will be measured in meters. Acceleration will usually be measured in meters per second squared, and then time will almost always be measured in seconds. Okay? So let's move on down. Basically, when you're dealing with kinematic equations, there's two scenarios that you'll run into. The first scenario I have marked here as number one is when you have something that's dealing with constant velocity, meaning that there is no acceleration in the problem. And if you're dealing with constant velocity, basically you have two equations, and they really are the same thing. Delta x, which would be the displacement in the x direction, is equal to the velocity times the time. Or delta y, which is the displacement in the vertical direction, is equal to velocity times time, another equation you may be more familiar with is speed equals distance divided by time. That's basically what these are, it's just they're manipulated in a different fashion. Okay. Now that's easier, at least I think. The second type of equation or problem that you'll run into is one that has a changing velocity, which means it has an acceleration. The second you have an acceleration in a problem, these two equations up top here become invalid. They don't work. And so we have to use some different equations, which we can look at those down here and see them in all their glory. Here are the four kinematic equations, and in the column on the right, I feel like this is actually very useful. It mentions the missing variable in each of these equations. So this first equation right here has no final velocity in it, which is a beautiful thing, because if the problem doesn't give you a final velocity, and if it's not looking for a final velocity, then you don't have to worry about it, and this would be a good equation to look for or use for that problem. And that same is true for all four of these. They all are missing a variable, and basically that's a way to kind of help you look at which equation you need to use for each problem. Okay, so these equations I actually recommend either memorizing or writing down on a note card or having in a place that's handy so that you can access them easily. There is a four-step method to solving kinematic equations, and until you get really good at it, I highly recommend following this method. The first step is draw the object's path, so draw a picture of the situation, labeling the initial and final positions, and then draw in your velocity and acceleration vectors. The second step is decide what directions are positive and what directions are negative. Typical sign convention has it that right and up is positive and down and to the left is negative. The third step is you need to identify if A being the acceleration, is 0 or not. If it's 0, that's great. You get to use the easier equations that I mentioned above. If you have an acceleration, so A is not 0, you need to write down the 5 kinematic variables that we talked about in the beginning of this video, and then underneath each variable, write down the given values that the problem gives you, including the sign. And I highly recommend writing positive in front of the positive numbers and negative in front of the negative numbers. It really helps you not lose your signs as you're going through the problem. Then I recommend indicating the question that the problem is asking with a question mark. So which of the 5 kinematic variables is the question trying to get you to solve? So you know exactly what it is you're looking for. Make sure you use consistent units throughout the entire process. So if you have something that's in centimeters per second for like a velocity, and then they give you a distance in meters, you have to convert one of the two so that you're comparing apples to apples. And then basically, once you know 3 of the kinematic variables, you can choose one of the above equations and then start to plug in and solve. You just go and plug and chug at those babies. So here are 2 example problems that I've gone through. And I've already solved them just to kind of speed up this video. But I started off by kind of drawing a picture. Here's the starting point. I just represent it as a dot. And it's moving to the right, and we'll call this the ending point here. Okay. It says a car starting from rest accelerates uniformly at a rate of 4.9 meters per second squared. What is the car's speed after it has traveled 200 meters? So I drew a little picture, And I drew in the acceleration and the velocity vectors. This car is accelerating to the right, and its velocity is to the right. And so both of my numbers, acceleration and velocities, would be positive if I wrote them down. I also indicated a directional piece where to the right and up is positive, and that's just a way to kind of help remind you what direction the signs are relating to. Then I wrote down my 5 kinematic variables, and I wrote in what I knew. I knew the initial velocity was 0 because it starts from rest. I knew the final velocity was the question that I'm looking for, because this is what's the car's speed after it has traveled 200 meters. So that's the question. I wrote that with a question mark. I knew that the acceleration of this car was plus 4.9 meters per second squared. Notice how I put the plus there. The time they never give me in the problem, and they actually frankly never ask for time in this problem, so I'm not going to worry about it. And then delta x is the displacement of this car, and they tell us that it's positive 200 meters, which is given right here. So then I go and look at an equation that I want to pick out, and this one looks pretty good to me because it doesn't involve using time, and it will give me a v final. So I go through and I plug in what I know, and I get a final velocity of 44.3 meters per second, and I did put positive on it, just again to kind of indicate that it was probably moving to the right at the time when we were solving this problem. Let's take a look at another example problem. It says an astronaut standing on a platform on the moon drops a hammer. If the hammer falls 6 meters vertically in 2.7 seconds, what's its acceleration? Well, again, I start off by kind of diagramming the picture, and I don't have a real great diagram here, so I'm just going to draw another one. Let's say this is the diagram. I drop a hammer and it falls down to the floor, and here's the floor. My acceleration vector is directed downwards. My velocity vector is directed downwards, and that's good. I just kind of have an idea that everything's moving down. I decide what direction positive is, and positive is to the right and up, and I recommend using that all the time. Then I write down my 5 kinematic variables because there is an acceleration in this problem. They're actually asking, what is the acceleration? So I wrote down the 5 kinematic variables. My initial velocity is 0. My acceleration, I don't know. The v final, they don't ask for and they don't give me, so it's kind of like the unnecessary variable that I don't really need. The time is 2.7 seconds, and my delta y, or the displacement of this hammer, is -6. And you may say, why negative? Well, because it started up at a high point and then it fell down, so it'd be -6. Then I choose an equation. I choose d equals vi times t plus 1/2 at squared. I plug in what I know, and then basically I go through and I solve some algebra. And I get, in the end, an acceleration of -1.6 meters per second squared. Hopefully that helps you a little bit with this class discussion. I will talk to you guys next time.